This is a set of watchmaker's turns made in the probably the 18th century, and you can see some rough casting marks here and there. It's places where it was made by hand. And you can see that the bar was made by casting. You can see imperfections, and you can see marks from draw filing it to make it flat. And it's certainly flat to 18th century standards. But now I'm going to look at the technique that would have proven the flatness to a higher standard. The first thing we do is mark the surface. We're going to mark it with this dry erase marker. They have die chem, regular chalk will work, pencil, anything that marks it. The dry erase is very nice because it's not messy. And now we're going to take a real reference standard If we didn't have a reference standard, we could use the rule of 3 with 3 different standards, 3 different pieces to create a standard using this method. What we're going to do with our reference standard is just rub it. Now we can get some low points. This right here is obviously a low spot. Down through the center, you can see that some of the ink is still there, and this is obviously a very low spot as well. It's pretty accurate. But I can take a pencil here and mark the places that are actually high spots. There's a high spot right here. There's high along this. Now, if you want to see what this does with the gauge block, I'll do the same thing. I'll cover it just quickly with some paint. And we'll take another gauge block and see if there are any high spots on this that we can detect with that. So now we'll just rub it with a second gauge block. You can see it took all of the ink off of it, indicating that there are no low spots on this, that this is as accurate as the other block. If I wanted to make 3, I could do that easily. Now, another thing with these blocks is this end piece. This is a 4-inch block, and it is about as exactly as you can make it, 4 inches from one end to the other. Now, as we said, the end piece, the end part on these, is incredibly flat. So much so that if I press them together firmly and twist them so that it forces the air out, they stick together. The one block sticks to the other. They do that not by magnetism, because there's no magnetism at all, but by molecular attraction. Of the one piece to the other, because the surfaces are so perfectly flat, they fit so perfectly. So ringability was one of the tests in the 19th century that proved a level of flatness to, say, millionths of an inch. So here's a set of gauge blocks. These are the crowning achievement. These are actually C.E. Johansen blocks made by Brown and Sharp, probably somewhere in the 1920s or similar time. And here's a Pratt & Whitney block. These are very, very accurate, very, very precise. The lengths are accurate, and the flatness here is accurate. Now we're going to look at another system that is even more precise. This is a set of optical flats. These are made of quartz glass. They are, which is has almost no expansion with temperature, and they are flat, demonstrably flat to an incredible degree, 2 millionths of an inch, a 10,000th of a millimeter, or a tenth of a wavelength of light, something on the order of that. So let's see how you use these. Here, I have a laser connected to a tin can that serves as a diffuser so that I get monochromatic, one wavelength of light diffused this way. So now what we can do is we can take one of these, put it on top of the other one, like that. We get lines. You can see the lines there pretty nicely. If I press, angle it, I can change the size of the lines. You can see also that the lines are pretty straight. In fact, very straight. The straightness of the lines determines how accurate the flat is. So the height of the waveform right here is 630 nanometers. And the distance between the lines represents that 630 nanometers. So this is a good, easy way to measure 630 nanometers, or about 20 millionths of an inch. Here we have a microscope slide, really a very pretty nice looking slide. Precision ground. Should be very flat. We'll see if it is. You can see that the lines are not straight. In fact, they go all over the place. And of course, as I push it, it deforms as a thin piece of glass would be expected to. So this is an extremely sensitive test, extremely sensitive way of measuring how precisely something is made flat, and is the basis for a tremendous amount of technology. So here we have the watchmaker's turns, which served to make concentric cylinders until the well into the 19th century. Still occasionally used. The bow rotates the workpiece between these 2 points, and the graver held at the right angle can make the cylinder. Very crude, but quite effective. This is a watchmaker's lathe, which I've chosen to discuss because watchmaker's lathes are very, very simple. You have nothing more than a motor, a belt, a headstock, a very accurate bed, a tool rest, and a tailstock with a little center or whatever tool you want in it. You unscrew this piece on the end, now a lathe like this can do a pretty good job at making all of our standard shapes. This is a graver, a very sharpened edge on it. You can see I can turn things down very, very accurately, especially if I get a little closer. So now we're making concentric cylinders. Here we have this, which is a fixed length radius has a little center right here and a cutter on this side. And we can use it so our radius goes in there. And with care, we can create quite an accurate spherical surface. This is my theory as to how screw threads got their name. By wrapping a thread carefully around a shaft and filing, again with the head locked. We could follow the thread. Creating a crude thread. As we followed the string, off. Of course, now we use much more creative methods, taps and dies, for example. You can see a thread is starting to form itself, matching the pitch of the string. Every screw is a copy from another screw. So the question is, if every screw is a copy, how did the first precision screw get made? And I think I am going to show the answer. Something that hasn't been tried, I imagine, for 200 years. So what I do is I have this right here. This, of course, is a piece of PVC. And this PVC can be cut by this knife. made the knife, sharpened it to fit pretty well on the PVC. And the idea is that if the PVC is at a particular angle, if the knife is at a particular angle, it will dig in, cut, and make a thread, and make a thread, which can then be followed with some other tool, either to make it better or to copy it. Now, this was done by Henry Maudslay in the late 18th century, and I suspect by Jesse Ramsden also in the late 18th century. So he would have used copper instead of the PVC. This piece I'm not going to use, I hope not to use. Instead, I'm going to try with this piece, which I've put some black paint on, so that hopefully we'll be able to see, as you see here, a white line indicating the thread. So we're going to go try it, see what happens. So here we have a nice piece of PVC with painted black, with a little fitting centered up, and a nice knife, which I can set at whatever angle. And now I'll go ahead and set the angle. Where did I put that protractor? I thought I brought it out with me. There. Now we're set to try this. The idea is, I press down on this. This is at 1/2 degree. I should get about 30 threads per inch this way. So let's see what happens. Well, it's not working. Well, even though I didn't think it worked, I did manage to get a little bit of a crude thread on there. The PVC is a little too hard. My knife wasn't quite sharp enough, and the carriage on my lathe was too stiff to do a really good job. But it did work a little bit. And at least I tried. So that's how they made threads when they didn't have any threads. At least that's how I think they did. So the trick is to make sure you have an integral number of threads around here. So this is 16 threads per inch. So my calculations say I have to make this 1.79. So that's what we're going to do. We're going to trip that down till about 1.79, and we'll see if we can do this. So here we have it. Here's the piece right here. Here's the tap. And now we'll see if we can actually make this work. It should, in theory, gash a thread into this surface here, which will then make a very accurate angle measure. Needs a little bit of help. As you can see, it's working pretty well. Of course, if you don't get the diameter right, the next pass will wipe out the threads instead of making them deeper. But apparently I got the diameter close enough to right to make this work. So with that tap, I was able to make this gear. Now with this technique, I can build something that will make any size gear or graduation, whatever, with very good accuracy. The thread we know now is very accurate. This is very accurate, and it makes a rotational angle of tremendous accuracy. So here is our little gear gashed quickly, about 10 minutes. You'll notice I have right here a little mark. I have on top of the thing a little mark. So let's see what one turn of the thing does. And you can see one turn moved tiniest little bit, actually a 90th of a turn, because there's 90 pieces there. And there it's moved twice. So 360 degrees on this translates into 4 degrees here. Obviously, with a bigger one of these, we get even more reduction, allowing us to produce any sort of gear or graduation desired. Any angle can be produced with this. And this is how gears are made now.